We will learn differentiation of trigonometric functions. For this, we start solving the differentiation of trigonometric functions using first principle. For an example, we have a function f of x is equal to sin x. So this is the function, and we need to differentiate it using a first principle. We know that the definition of the differentiation is the following, that the derivative of this function f of x is limit h approaches to 0 f of x plus h minus f of x divided by h. And in the last lesson, we learned that this is actually the gradient of this function. So now we have f of x here. What we actually also need the function f of x plus h. So that will be equal to the sin x plus h. So this is a double angle identity. So we can write it in the following way, that the sin x times cos h, so plus cos x times sin h. So now we put f of x and f of x plus h in the definition, and our answer will be following, that we will have f of x, its derivative, that will be equal to the limit of h approaches to 0. We have sin x times cos h plus cos x times sin h minus sin x, and all of it divided by h. So here we can see that in the first term and the third term of numerator, we have a common factor, sin x. So here we can have limit h approaches to 0, then this sin x is common, and we left with the cos h minus 1. The second term of numerator is a cos x into sine h, all of it divided by h. Now we can write this fraction in the form of two separate terms. So the first term, it will be sin x times cos h minus 1 divided by h. So we write first sin x and then apply the limit h approaches to 0 to cos h minus 1 divided by h. The second term, it will be plus cos x and limit sin h divided by h. Now here in the first term, we have the cos h, and then the second term, we have a sin h, and a h approaches to 0. So it means we can use small angle approximation. What the small angle approximation is, that the small angle approximation is that the sin x, that will be approximately equal to x, meaning that any angle. So let's use here theta to, so then sin theta is approximately equal to theta, and cos of theta, that is 1 minus 1 over 2 theta square. If we use this small angle approximation in our this last expression, then we will left with the following, and that is the derivative of our function is equal to sin x times the limit h approaches to 0, and here we will have a 1 minus 1 over 2 h square minus 1 divided by h, and the second term, that will be the cos of x, then limit h approaches to 0, and we got h divided by h. So now here we can see very easily that this 1 gone with this negative 1, and this h goes with the h, and this is 1. So here in our first term, we will left with minus half of h square divided by h. Then this h will actually cancel with one of the powers of h, and we will left with the following expression, that is the f of x first order derivative, which is sin x, and the limit h approaches to 0, and negative half h plus cos of x. Now we apply the limit on this first term, and then we will get here 0. 0 times sin x is 0. So our actually the derivative is equal to cos of x. So it means that if we have a function f of x is equal to sin x, then its derivative, first order derivative, is equal to cos of x. Similarly, you can also prove that for a function f of x is equal to cos of x, the first order derivative f prime of x will be equal to negative sin x. So it means that the derivative of sin x is cos x, and the derivative of cos x is negative sin x. Now we will solve a few questions, and then we will move ahead towards exponential functions. Okay, now we move ahead towards differentiating exponential and logarithmic functions. So for this, we consider a function, and the function is, let's say we have f of x is equal to e power ax. So here a is a constant. And we know for the definition, we also need f of x plus h. So that will be equal to e power a, and x will be replaced by x plus h. So now we use the definition, and this definition is the first order derivative of a function is equal to a limit h approaches to 0, f of x plus h minus f of x divided by h. So now we put both of these functions in this expression, and we get h approaches to 0, e power a into x plus h minus e power a x. So remember, this a is a constant number. So now we will have a limit h approaches to 0. Then here, this first actually term of the numerator, we can split it into e power ax times e power ah, because these both powers are adding up. So then we will have a negative e power ax divided by h. So now we have a common factor, and this common factor is e power ax, and then we will apply the limit h approaches to 0, and we left with e power ah minus 1 divided by h. So here, actually, we need to use identity of this exponential function, that if we have e power theta, that is equal to 1 plus theta plus theta square divided by 2 factorial plus theta cube divided by 3 factorial, and so on. So if we use this identity in our this expression, then we will left with the following expression, that the derivative of our function that must be equal to e power ax, then times here that the limit h approaches to 0, and now because we have e power ah, so then our answer will be 1 plus ah plus a square h square divided by 2 factorial, and the higher order terms, the last term -1, which is over here, then all of it is divided by h. Now we can see here that this 1 has gone with 1, and we will left with the terms, and all of these terms actually have a common factor h, and that common factor h of each term will be divided, or you could say cancelled out with this denominator h. So we will left with e power ax, then the limit h approaches to 0, and here the first term will be a plus a square h divided by 2 factorial, and then here it will be a cube h square divided by 3 factorial, and the higher order terms, and each term will have h. Now, if we apply this limit h approaches to 0, then every term will be 0 except this first term a, and that will be multiplying with our first factor e raised to power ax. So this means that the derivative of our exponential function e power ax, that is a times e power ax. So here you can actually also prove using the same method that if we do have a function which is an exponential function f of x e raised to power x, its derivative, first order derivative, is equal to e power x as well. And if we have a function where we do have e power a constant k divide times by x, then its derivative is equal to k as a coefficient e power kx. So in fact, actually, you can actually see here that what you do have when you have exponential function, its derivative is the same, then it means exponential function and the gradient of the exponential functions are the same. And then another point that you must actually keep in your mind is that here, when you are differentiating these kind of functions, e power kx, so this is simple, that exponential function have the same derivative, then the power will also be differentiated. So the derivative of kx is k, which is over here, that what we can also prove using this first principle. Now, let's solve some logarithmic functions as well. Now, we will differentiate logarithmic function. So for this, we presume that we have a function f of x is equal to natural log of x. So this function, we can also write it as a y is equal to natural log of x, and this natural log of x can be converted into the exponential form, meaning that this will be e power of y that is equal to x. So now this is our expression number one. If we differentiate it, then our answer will be that we just proved that exponential functions, their first order derivative, their derivative is actually the same. So we will get e power y then times dy over dx, because our this function is actually the function of x, so we want to find dy over dx. So y is a dependent variable, so we will have dy over dx here, that is equal to the derivative of x is equal to 1. So now you can rearrange it. So dy over dx is equal to 1 over e power y. And we know that e power y is equal to x. So the derivative dy over dx is equal to 1 over x. So similarly, you can actually also see that if we do have a function f of x is equal to natural log of ax, then what would happen? So here, this is y is equal to natural log of ax. Then this will be equal to that e power y is equal to a times x. And now we differentiate it e y times dy over dx, that is equal to a. The derivative of x is 1 and a is its coefficient that will remain as it is. So now what did we get? That dy over dx is equal to a divided by e power y. So e power y is equal to ax. So dy over dx is equal to a divided by ax. So here you can see that the a has been actually cancelled out with the a in the denominator, and our answer is equal to again 1 over x. So here the learning point is the following, that in case of logarithmic functions, that if we do have a function f of x is equal to the natural log of x, then its derivative is equal to 1 over x. And even if we do have a function where we have a natural log of ax, where a is a constant, then the derivative will be still the same, just 1 over x. Okay, so this is actually a very simple method and very simple formula to remember the differentiation of logarithmic functions. So here we have actually completed the differentiation of trigonometric function and the differentiation of exponential and logarithmic functions. So we learned the formulas, and we also learned that how we can prove using the first principle. So now we move ahead towards solving some questions. Okay, let's start some questions. Here we have Q1. This first question is that we have a function y is equal to x square plus 4 times cos 3x. So we need to find its first order derivative. So that will be dy over dx. So we can see that it is in the form of a polynomial. We have two terms here. So we can differentiate both of these terms separately. So the derivative of x square is 2 times x, because this power will become coefficient and the power will reduce by 1. Now, then the next one we have here the constant term 4 that will remain as it is. Then we have a cos 3x. Then the derivative of a cos is a negative sin, and the angle will be still the same 3x. And then we also actually need to take the derivative of this angle, which is a 3x. So derivative of 3x is 3. So we will times that 3 with 4. So answer is 2x negative 12 sin 3x. So here, this is actually this answer of our this a very, you can say, simple question. So here there is one thing that you need to remember, that when you do have a trigonometric function and this angle is actually is also like a function, so then you also need to differentiate the value of the angle. So in an other ways, you can also remember in a way that if we do have sin x, so we are actually differentiating it in the following way, that the dy over dx is equal to the derivative of a sin x is the cos x, and the derivative of x is equal to 1 times cos x, that will remain as it is. But if we do have the function y is equal to sin kx, then we will have the derivative of this function dy over dx, that is the cos kx, and the derivative of kx is equal to k. So that is very simple to remember as well. What you can also prove it using chains rule that we will learn in our next lecture. So now we have another question to solve, and this question is the following. The question is that find the gradient m of the curve, and this curve is y is equal to 2 times sin 4x negative 4 times cos 2x at the point of at the point where x is equal to pi by 2. Now we need to solve this question. So you see, what do we need to find? We need to find the gradient. And this gradient is actually simply the first order derivative of our function, and this function is given. So it means that what we would do first, we will actually find the first order derivative of this function, that is dy over dx. 2 is constant, that will remain as it is, and the sin 4x, its derivative will be cos 4x, and the derivative of 4x is 4, that times with the 2, and we will get 8 here. So now we will have a negative, and the derivative of cos 2x will be negative sin 2x, and that negative will make this negative positive. Then the derivative of 2x is 2, 2 times with the 4, answer is 8. So this is actually the gradient of our this function. What we need to find the gradient at x is equal to pi by 2, so we can actually substitute the value of the x in this equation of the gradient. So then our gradient m of this function should be 8 times cos 4 pi divided by 2, then plus 8, then here it is sin 2 pi by 2. So these are the values. Then here this 2 gone with the 2, and we got cos 2 pi. So cos 2 pi is 2 pi is actually positive 1 because this is actually the cos graph. So we know that the values of cos actually at the 0 it is 1, then at 90 it is 0, at 180 negative 1, 270 are 3 pi by 2, and then is 0, and at 2 pi it is 1. But in case of the sine, it is actually 90-degree phase shift. So that will be going like this. So now the sin pi, because 2 has gone with this one, so then our this second term is 0. This cos 2 pi is equal to 1. Then the gradient m must be equal to 8. So in this way, we can actually find the gradient of any given trigonometric function. So now we also solve a few questions from exponential and logarithmic part. Okay, now we have another question. Let's say this is our question number 3, and our function is y is equal to natural log of x power 3 plus natural log of 7x. So we learned already that the derivative of natural log of x is 1 over x, and even if it is natural log of kx, that will also be 1 over x. So here we can see in the first term, we have a natural log of x power 3. Here we can use identity of logs, that the power that becomes the coefficient. So then it will be 3 times natural log of x plus natural log of 7x. So further here, you can actually also split this natural log of 7x, that will be natural log of 7 plus natural log of x. So natural log of x, natural log of x, so that will be 4 times natural log of x plus natural log of 7, that is our y. Now the first order derivative dy over dx, that will be 4 over x, and here the natural log of 7 is a constant term, so its derivative will be 0. So you can actually also solve this question like this. It is very simple and straightforward. Now we have another question, and that question number 4 for an example, that our function y is equal to 2 negative 3, and this is exponential e power 7x, and the common denominator is 4 times e power 3x. Now, to solve its derivative, to find its derivative, what we need to do, we actually split it in the form of two separate terms. Then we will get 2 over 4 e power 3x negative 3 e power 7x divided by 4 e power 3x. Now let's simplify these both terms a bit more. 2 over 4 is 1 over 2, and we can write it as a e power 3x is negative 3x, then negative 3 over 4. we have a 7x in the numerator and 3x in the denominator. So we will left with positive 4x. Now both of these terms are simplified. We can very easily find their derivative. So what the rule is, the formula was that if we do have a function and this function is e raised to power kx, so then the derivative will be equal to k e raised to power kx. So you can say that our at the first order derivative of this expression dy over dx will be equal to 1 over 2, and this is the exponential function, and it will go as it is e power negative 3x times the derivative of the power. So you can also remember it like this, and which is actually more logical. And then we will have the next term, which is negative 3 over 4 constant remains as it is. And the derivative of exponential function goes as it is times the derivative of the power, which is 4x. Derivative of 4x is 4. Now we can simplify it, write it in a simplified form, negative 3. So that will be negative 3 over 2 e raised to power negative 3x. Then we will have a negative 4 gone with the 4 is 3 e raised to power 4x. So you can also leave it as it is. So that is our derivative of a given function. Now, here we take one more question, and that question is that for an example, we have a function, and this function is following question number 5. Let's say that we have a function y is equal to e power 2x negative natural log of x. And we need to find the gradient m at x is equal to 1. So we know gradient is the first order derivative of the function. So dy over dx, that will be equal to the first term, its derivative, exponential function as it is e power 2x times the derivative of its power 2x. The derivative of 2x is 2. Now negative derivative of natural log of x is just 1 over x. Now we can put this value x is equal to 1, and we find that the gradient m of this function will be 2 times e power 2 times 1 is 2, and negative 1 over 1 is 1. So it means gradient is over here e times sorry, 2 times e power 2 negative 1, that is the gradient. So you can use the value of the e, take its square, times it by 2, and take away 1. That will be the final single value of the gradient of this function. So today what learned, we learned about the differentiation of trigonometric functions. Basically, in this lesson, we were focused only on the sin and the cos functions, and then on we moved towards the exponential and logarithmic functions as well. So in the next lesson, we will move a little bit further towards other trigonometric functions and chain rule as well. Thank you very much for listening.